But without further ado, Justin, I will hand the mic over to you, sir.
Thanks, Matt. I certainly appreciate it. And first off, I want to thank Typhoon for letting me present. It's not often that protection engineers get to pass along some of the wisdom learned out in the field. So it certainly feels good to do that, to pass it along to you folks. I'll start off with kind of a quick introduction with myself. I'm a former utility standards engineer. I was in a protection standards role at a utility. It was Duke Energy, and focused a lot in the DER protection space and system standard space. I left there and went out on my own and started my own consulting firm. We specialize in advanced inverter modeling, like hardware in the loop type of simulations, DER, PNC studies. T&D, so your transmission and distribution islanding, which is a fairly hot topic right now within the industry. DER settings development, also pretty big topic within the industry. 1547 and the like, changes there. Ride-through has gotten to be pretty big. That's also a pretty big heavy hitting area I see a lot of utilities struggling with right now. Not a lot of books written on this subject, so there's quite a bit going on there. Arrestor failure, ground fault overvoltage, and effective grounding analysis. That counts for microgrids, which I have experience with, and also your grid tied stuff as well. Transient simulations, and like we said, there's other stuff too I do as well, like hardware in the loop simulation in real time with DVARs and other things as well. We also go into DER reclosing strategies on both the transmission and the distribution side. So a lot of utility folks, I can certainly understand your plight. There's a lot going on there, a lot of information coming to the surface as we get more DER in the system. So just to kind of dive right in and talk a little bit about modern relay testing. As you guys will know, and this shouldn't come as a big surprise, is that modern microprocessor relays have gotten really complicated. Firmware changes and the like have really complicated the device. It helps a lot. It hurts in some areas. It makes it difficult to test. But most people, I don't think, including myself, admittedly, when I first got started at this, didn't really think of hardware in the loop as something that applied to protection testing. As Matt kind of alluded, I thought it was kind of something different. I guess viewing it from the lens of a PNC engineer, I didn't really think it was very applicable, but we'll talk a little bit about that. So as far as my business goes, we're getting a lot of involvement in customers that are asking to test schemes that are 10 plus relays. We were talking earlier about a scheme that had 28 relays in it for automatic switching and self-healing systems. You know, do you want to take 10 test sets out into the field and test that? It becomes really cumbersome and very difficult to do that. Some of these systems are in underground space, so getting a satellite clock and synchronizing, there's all kinds of areas where you wouldn't think there would be a lot of complexities, but it gets kind of bird nested, if you will, trying to figure that out. And I'm getting a lot more customers asking about HIL and kind of inquiring about what that really means and how they can use it. I think for me personally, I think the industry is kind of reaching an inflection point where just kind of conceptually, where test sets, like your simple current voltage source, I mean, that's basically kind of what a test set really is. It's a current amplifier and a voltage amplifier, are not working well to test these 10 plus relays, these really complicated schemes. On the right, I've got a picture of a forward and reverse direction logic in an SEL 411L. It's very complex. To try to test this, I mean, is weeks to really get into it and dive deep into the subject matter. So definitely no short order there. So by the numbers, this is kind of interesting, which I took from the folks at NERC. So I want to tip my cap to them. I took some historical data from misoperations in the past. The first one is the Texas interconnection. They cite a 35% misoperation 35% of all their misoperations, excuse me, are logic design and incorrect settings, which is that's pretty large. You know, you've got some other aspects too, DC systems, switching due to personnel errors. There's other aspects. But that's a pretty big chunk. A third of it's logic design and incorrect settings. NERC was almost close to the same, 29%, so about a third of all misoperations were the same thing, logic design and incorrect settings. For me personally, I actually went back and looked at all the business that we had this year, and as far as microgrid and DER misoperations that we were involved in reviewing, and we came to about 2/3, maybe a little bit less, could be traced back to logic design and incorrect settings. And I will say, just kind of looking back at distributed generation, specifically microgrids and even grid tied stuff, utilities aren't catching this kind of stuff using test sets. It's just not working for them. I think it kind of points to a bigger problem, that the relaying is becoming so complex, it's just becoming very cumbersome to test it with a test set. Not that there's anything wrong with that. You know, test sets have their place. I have one at my business and I use it all the time, but there are times when it doesn't quite apply. So I think it kind of points to a general overarching thing, that there's something kind of wrong in the industry. So I think for me, and I always get a kind of a chuckle out of this, I do better with an example. So I'll give you guys an example of a microgrid case study I had where we were doing hill simulations, and I think this built a good case of something simple that kind of turned into something larger. It kind of points in a direction that test sets, applying that test procedure like that using test sets, HIL gives you a little bit more of an advantage there, diving deeper into that complicated protection. It makes it easier for you, and I'll kind of show you why. And I always get a laugh. One of the younger engineers I was working with, we had put a fault on the system, and he turned around and looked at me, and it had been running for 10 seconds with a fault on it. He said, "I think that relay was supposed to trip." So I got a little bit of a chuckle out of that. Of course, that was in a simulated environment. We wouldn't have been laughing had that been the real thing. So we were very excited we caught it before it got too far. So here's kind of a simplified one line of the system we were working on, and I kind of boiled it down to a simplified system. It was a 12 kV network. You had a point of interconnect recloser that tied back to the utility system. You had some pretty simple loads, and there was a battery energy storage system on the network that was part of the microgrid, and it had a grounding transformer that was a Y grounded delta. This utility had chose that over a zigzag transformer for various reasons, but the best transformer was around, or best unit was around 5 megawatts, I believe. So the HIL scope of study was to kind of move a fault around in the network. So slide a fault throughout the microgrid and observe the results. Did the right protection operate? Did things coordinate properly? Are we seeing anything that's not desired? Did something not trip when it was supposed to? Any major things that we need to follow up on? So that was kind of the scope. Pretty simple as far as it goes. Various fault types were considered: single line to ground, phase to phase, etc. These settings had been in service for several years, and the utility wanted to know if there was anything they needed to be overly concerned about. One big thing was that the field technicians had been involved with testing the relaying out in the field. They felt pretty comfortable with it. It had passed a lot of their tests they had thrown at it. So, and they sent us copies of those reports when we looked at them, and took that data and kind of rolled it back to a study. So what we wanted to focus on, the utility was particularly concerned about, was the grounding transformer. Was the grounding transformer adequately protected? And we'll go a little bit into that. That's a particularly vulnerable item within microgrids. So like we said, grounding transformers are particularly vulnerable. And why is that? So what I found is, I mean, not a big surprise here, but we all kind of know implicitly that inverters supply very little fault current availability compared to rotating machines. So it makes internal faults within transformers very difficult to detect. specifically bushing failures too. I've seen 2 cases in microgrids where the bushings have failed on a transformer and the protection did not operate. It was actively arcing in the field. The technicians reported it and actually had to manually clear the microgrid, and none of the protection operated. So there has been several cases I've seen where this has happened. And most of that can be traced back to either logic and settings, like we said before, or just the fact that it was so low a fault current, it was very difficult for the relaying to detect that. One other thing I think that people miss that I always like to pass along is I think transformers in a microgrid are exposed to voltages and frequencies that are not typical in a utility system. The frequencies are very highly regulated in a utility system when it's grid connected. Utilities do a great job at that. In a microgrid, when you have droop controls and other things like that, not so much. They're getting exposed to things that are a little bit more atypical, so you're going to see higher failure rates, and that's what we are seeing. We're seeing higher failure rates with that. So what do we do about faults down in this transformer? So inside the grounding transformer, what do we do? How do we protect for that? You know, a lot of utilities want to know that. What can we do to protect it? So protecting the grounding transformer, like we said, with no utility source is pretty challenging. There's not much ground fault current contribution from the inverter, so it makes it really difficult. So a lot of companies have gone with something called REF, which is restricted earth fault protection, which is really, really good. As far as simulations go and real world experience, I have seen where this has been really, really good. I've seen several instances where it tripped when it was supposed to, and there was actually an internal fault in the transformer. It worked perfectly in a microgrid setting, so that was pretty good. I've seen this work pretty reliably, so that was always good to see that. That protects specifically the Y grounded winding. On the delta side, there's a classical ungrounded circuit protection, which is your 3V0, zero sequence over voltage. That's what a lot of folks are using for that side of the transformer to protect for ground faults. They'll install PTs on the secondary and then monitor that using a protective device. So we'll talk a little bit about getting into the protection aspect. We'll talk a little bit about what is REF protection. It's a pretty misunderstood thing as far as protection engineers, even within the community, goes. REF is a ground directional element that detects faults deep inside the winding, and that's kind of a fancy way of saying it's a current angle comparator. So what it does is there's 2 sets of CTs on a transformer. There's a set on the top of the bushing and at the neutral, and the top CTs are summed together where you sum up your phase currents and you can get the effective ground current contribution into the transformer, and then you have your neutral measurement. And what it's doing is it's comparing the angular difference between the two. This is kind of a simplified way of looking at that. And like we said, the simulations, myself using the Typhoon and other stuff I've done too within MATLAB Simulink and some of the stuff we've seen in the field, as far as data collection, show that it's really worked pretty well. The reason it works well, at least from what we're seeing out in the field experience, is because it's using angles rather than magnitude. And that's an important concept I think that a lot of people miss. Overcurrent coordination and overcurrent elements work great for utilities because there's so much fault current availability. With inverters, not so much. It just doesn't seem to work real well. There's other items like voltage restrained overcurrent that you can use, and those do work well. There's times when they don't work so good, but this works well because of the angle comparator. So it's operating on angle rather than magnitude. So here's kind of what you're going to see. If you went and placed a fault external to the grounding transformer, what you're going to see is if you went and grabbed the data from the relay itself and you compared the angle difference between the ground and neutral measurement, so your CT here, summing at the top, and then your bottom measurement here, if you measure this angle, it's about at 180 degrees roughly. There's going to be a little bit of difference there just from measurement error and other things, but you're going to see a large angle here for external faults. For internal faults, you're going to see a pretty narrow angle here is what you typically see. And I'll give you guys some examples of actual data we collected with the HIL showing this. So this is kind of what to expect. So keep that in mind as we go through this. You know, you see a wide angle at 180 degrees, that's an external fault. You start seeing these narrow angles like this, it's an internal fault in the transformer. So that's what the relay is using as an operate quantity. So let's prove this thing actually works. Me in particular, I like actually seeing it when we do the simulation, so which is pretty cool. So here's a hill test we did with Typhoon, and we ran an internal fault test. So let's prove it works. So we placed a fault near the top of the winding. It was right at the very tip inside of the CT, just inside the CT. Wasn't like deep inside the winding or anything like that. And like we said earlier, you would expect to see this angle be fairly narrow. During this simulation, it was the recloser was closed, so the point of interconnect was tied back to the utility, so it's grid connected at this time. So this is kind of what we expect to see, a pretty narrow angle here. So for you P&C engineers, I took the time to draw out the positive, negative, and zero sequence networks. I won't focus too much on that. It's kind of a vision test a little bit to go through each one of them. But I grabbed the phasor quantities from the relay, and here's what we got. So as you can see, the angles as we expected are pretty narrow, indicating that it was an internal fault. And the relay did trip, so which was good. So REF1F, which is what the relay calls a forward fault, indicating that the fault is inside of the transformer. It did correctly identify it as an internal fault, and it did actually trip the relay. So it did operate for this internal fault. So let's move the fault. We said, okay, that's an internal fault. Let's slide it out on the network somewhere. So we'll slide it out. So now it's outside of the zone of protection. So this we would expect for it to restrain and not to operate for this particular case. We would expect to see, like we said, 180 degrees, so a pretty wide angle between the ground and neutral measurements. As we slide it along somewhere in this network, even out onto the utility system, would expect to see the same thing. This was kind of close into the transformer from what I remember. It wasn't too far away, and it is grid tied at the time. So here's the measurement, and you can see it's almost exactly 180 degrees, which was good. That's kind of what we were expecting. And I went through and drew these out again. And as you can see, that not much of a surprise there. The reason for that is when zero sequence flows through this network, it comes into the polarity side of the CT and then is injected at the top in the non-polarity side. So that's the reason you're getting that wide angle there. And I'll kind of show you. This is a reverse. So we said forward was internal, reverse is external. So it was an external fault, so the relay blocked. It did not operate for this, which is good. That's exactly what we wanted to see. Customer was happy with that. That's exactly what we wanted. All right, well, without further ado, we're going to island it. So we went through the process of actually opening the switch, the recloser, and placing an external fault in the network, and then taking a look at what we had there. So as you slide the fault inside the microgrid, which is exactly what we were doing, we kind of expect to see this phasor quantity. So something kind of similar to what we were seeing before with it grid tied, which is exactly what happened. So the interesting thing with this is, and if you go and draw out the symmetrical components aspect of it, it's kind of the same thing. It's being injected into the non-polarity side, and then current flows, or into the polarity side, excuse me, and then it goes into the non-polarity side. But notice that the magnitudes are almost nearly the same this time. So you don't have any contribution from the grid. So it's simply from the grounding transformer at this point. So the relaying at this point says, okay, yep, external fault. I'm not going to trip. And we did this several times. We slid the fault throughout the network and got the same result every single time. So which is good. That means it's correctly identifying external versus internal faults, grid tied and grid isolated. So I'm sure some of you are waiting for the other shoe to drop. So here we go. This is the one where this one kind of caught me off guard, truth be told. I didn't expect this result. So this was an internal fault with it islanded. This is the one that would be the most severe case. It'd be the one I would be most concerned with, and the utility was also most concerned with as well. So we opened up the recloser, islanded the system, allowed it to stabilize, and then placed an internal fault inside of the transformer. And you'll notice now that IG is gone. So why is that? Why is it that when we're islanded now IG is gone? So we only have IN, which is interesting because we said that that REF operates off of an angular comparison. So what happened? What do we do now? There's nothing really to compare an angle to. So what does the REF protection do? So without digging too deep into the symmetrical components aspect of it, if you place the fault point inside of the transformer and you draw out the circuit of the zero sequence portion of the circuit, what you'll find is IN is the only measurement, and that's exactly what we got. So when fault current flows, it only flows through the IN portion of the transformer, and it doesn't go through IG. So basically the current's coming up through the neutral, it's just not leaving the transformer, it's contributing to its own fault. It's not actually leaving the IG node to go into the microgrid. And part of that, or the exact reason for that, is the grid is no longer present. So this portion of the branch, if you were to put this shunt here, you would get a current flow through this portion of the branch, which we do not have because it's grid isolated. So you would expect to only see IN and not IG, which presents a problem. What do we do now? We said that we're doing an angle comparison. So how does that work if you don't have an angle to compare to? Well, this is the internal fault detection. It did not pick up. So what do we do? And the younger engineer I was working with, he said, I think it was supposed to operate here, and it sat there for a while. I was waiting for it to trip, and it never did. And it sat there for a good 10, 15 seconds running with a fault on it. So we kind of paused and said, well, what happened? I mean, the symmetrical components are lining up. What's the deal? Why is this relay not operating for an internal fault? So we kind of stepped back, took a break, and said, okay, well, let's do a Hill root cause analysis. What really happened? We ran a couple more faults, pulled the settings and dug into them in a pretty deep detail to kind of figure out what exactly had happened. And I was really surprised at how simple the explanation was, but the complexity that it caused, and some of the major issues it caused as well. So an REF system, when you go test restricted earth fault protection, every REF system has a bypass. It's there for a reason. It's there for this exact reason, to be specific. When it can't compare current angles, so like for example, when you're in a microgrid and the utility is not present, like we showed in the previous slide, and an internal fault happens, there is no angle to compare to. So SEL and other manufacturers have made something called REF bypass logic. And what that does is it says if I have IN flowing, so current's coming up from the neutral and it's contributing to its own fault and it's not leaving the transformer and going out into the network or some other network, that's unaccounted for ground current. So it's basically contributing to its own fault. So they wrote some logic in there that's saying basically not IG, so meaning there's no ground current flowing, and IN. And here's the kicker, you have to turn it on. So there's a bypass enable. And there's some reasons why there is logic to turn it on. There's a whole explanation behind that when they're used in other systems, such as auto transformers with secondary breakers on them. So, but the point is in this exercise that you have to actually turn the thing on for it to work. And we started digging into this logic and we said, okay, well, I wonder what happened here. So here's the REF bypass logic, and it was set to 0. So that was a pretty big uh-oh moment for us, where we said, okay, that's a pretty major settings error. It turned off this logic gate here, and the result of this was blocking a trip for an internal ground fault, which, for for a microgrid situation, it's already tough enough. That's a pretty big deal. That fault could persist for long periods of time, and it's a pretty major safety issue. So this kind of manifested itself in a way that was kind of a safety concern in the sense that there was no internal ground fault protection in islanding mode. So kind of a follow-up from this was we went back to the customer, talked to them a little bit about what our findings were and what our recommendations were. We went in and changed the REF bypass to turn it on. And the customer requested an immediate field change. So we went out, made the settings changes, and moved on from there. They also wanted a full review of other relays in the field. So they wanted us to go back and kind of dig into and make sure there was no other surprises that were going to come up, because this is kind of exactly what we were looking for. But one big thing I kind of took away from this was I took a look at the field testing data after this event occurred, and all the relays passed using a test set. I mean, including myself and 3 other engineers missed it as well. And this kind of goes back to what we were saying in the first couple slides, which is using a test set can kind of sometimes, depending on the complexity of things, this is a little bit more simple example, but it can give you a false sense of security. I think HIL helps you in that regard. That paradigm shift where you're setting up an actual network level simulation, so you can put faults inside of the transformer, and the phasor relationships and things like that are kind of figured out for you, so you can focus on the logic. So that 1/3 that NERC's reporting, you can focus on getting that down to much less. So like we said, enabling that REF bypass during the logic development was overlooked. That was a pretty big deal. That's obviously something we don't want, so that's why we're testing and we're trying to find these things before they get out into the field. And this was a pretty simple mistake that was often difficult to detect, and that's what I see a lot. If I had to pass along some advice to the folks that are in the utility industry and some folks that are in academia too, is a lot of times these things manifest themselves as very simple mistakes, like knots are missing or ands instead of ors. I mean, something kind of simple. I've even seen parentheses put in the wrong spot, and it messes things up. So the engineers often get it right, the idea behind it, but the deployment of it wasn't so good, and these simple things that end up turning into pretty major issues.